Swayam Prabha. Digital India. Educated India.
Now we will discuss the equations of equilibrium. We have discussed that on a body forces and moments act. Moment can be called as a generalized force. It has a unit of Newton meter. So, moment times the angular displacement gives the unit of work. Similarly, the force times the displacement gives the unit of work. So, moment can also be called a generalized force. Now, we know that moment is produced when there is a force present, that there is a force, you take its moment about a point O. So, fundamental concept is that force, there are forces acting and therefore they produce the moment. It is possible to replace a system of forces by some resultant force about acting at a point and moment. Now, we will discuss about that what are the basic equations of equilibrium which can help us to find out the relation between the forces and moments when the body is in equilibrium. A particle is, we have already discussed in the previous lecture that a particle does not have a size, but it may have mass. So, particle is just like a point, okay, which is not having a size, but this is this one. So, therefore, this will be a particle is in equilibrium if it is stationary or it moves uniformly relative to an inertial reference frame, and a body is in equilibrium if all the particles that make the body may be considered in equilibrium. So, like if this particle is moving with a constant velocity, then it is in a equilibrium. Similarly, there is a block, there are number of particles, in fact infinite number of particles, all of them are moving with a constant velocity. Therefore, this body is in equilibrium. Now, but however, it is not true for a rotating body. See, if this disc is there and it is revolving about perpendicular axis, then if we consider a typical particle here, this particle is not moving with a constant velocity, because the direction of its velocity keeps changing, although the magnitude may remain same if the angular velocity is same. So, therefore, naturally this particle is not in equilibrium, although the particle which is at the center, that is in equilibrium, it is not moving. Therefore, this body cannot be considered in equilibrium, because all the particles are not in equilibrium. So, a body is in equilibrium if all the particles that may be considered to comprise the body are in equilibrium. Now, one can study the equilibrium of a part of the body, whether this part is in equilibrium or not, by isolating that part for the analysis. Such a body will be called a free body. Okay, we make a free body diagram and then show all the forces from the surrounding that act on the body. Then that diagram is called a free body diagram. For example, if you consider a ladder AB which is resting against a wall and against a floor here, okay, this is in this case it is assumed that they are smooth, okay, there may be friction also, does not matter. So, this ladder AB is shown here separated from the wall and floor. Wall and floor have not been shown, only we concentrate our attention on the body AB, we only view these things and then we see what are the forces acting on this ladder. One is the its own weight due to gravity. So, therefore, W is the force passing through the center of gravity. Then you have the reaction of the floor, that is R2, reaction of the wall R1. These three forces are acting on the ladder. This is a free body diagram of the complete ladder. I could also have I could have made the free body diagram of half the ladder. That could also have been a free body diagram. So, like that we make the free body diagram, it becomes very easy to analyze that what are the forces acting. Here I see only the weight, because I am not aware that this floor is putting reaction here. Okay, because if the floor puts reaction here, this also puts equal and opposite reaction on that thing. So, free body, but when we separate that, we only see that this R2. So, now when a body is in equilibrium, the resultant of all forces acting on it is 0. Thus, the resultant force R and also the resultant couple MR both will be 0, and therefore, we have the equilibrium equations as R is equal to sigma F equal to 0 and MR is equal to sigma M, this is also equal to 0. These requirements are necessary and sufficient conditions. Okay, they are necessary, that means if a body has to be in equilibrium, then R must be 0 and resultant moment also must be 0. That this is necessary, that means this is, and if R is 0 and then moment is 0, then the body has to be in equilibrium, that means these conditions are sufficient also, we do not require any other condition. Let us understand equation 2.1 for different type of force systems, what type of forces can act on the body. One is the system of collineal forces. In this system, line of action of all the forces act along the same line. For example, consider a rope being pulled by two players. Suppose this is a rope and it is being pulled. One player is pulling like this, other is pulling like this one, and okay. So, in this case, that line of action of the two forces is same. The forces act along the same line. So, it is collineal. Now, this force may be F1, this may be F2, then the resultant force in the direction of pull of first player is F1 minus F2. F1 minus F2 is the resultant force. It should be 0. Hence, for the equilibrium, F1 is equal to F2. With this, the second condition, that is moment should also be 0, is fully satisfied, because moment of the forces about any point in the space will be of equal and opposite magnitude. Suppose you take the moment about this point also, then also it is equal and opposite, hence the resultant moment will be 0. So, this is thing. Then we talk about coplanar parallel forces. Coplanar means forces acting on a particular plane. We can make a plane on that only, this one, and they are parallel, like you have a plane on which the forces are acting like this. all forces are parallel to each other and lie in a single plane. Now, for example, you see this seesaw. Here one boy and one girl both are sitting on the opposite sides of seesaw. Now, if we just consider where the equilibrium of that seesaw. So, therefore, on the equilibrium, if we assume that seesaw is not having any weight, its own weight, then there is a fulcrum here, then in that case there is a, because boy's weight is W1, so it is putting a force on that is seesaw is putting a reaction on the boy. So, the if we make a free body diagram of seesaw, so therefore, this is acting in turn the boy is providing a force W1 on the seesaw, that is the thing. So, this is W1 and similarly the girl is putting a force W2 on seesaw, and then we will have at the fulcrum, we will have the reaction force of the fulcrum also. So, this is the thing, but that these two forces are parallel, that means W1 and W2 is vertical, therefore, the reaction should also be vertical. So, this system is coplanar parallel forces. Two, if the weights are both and they are sitting, if the boys are, if children are sitting at a distance of W1 and W2 and they are sitting at a distance of D1 and D2 from the fulcrum, then for equilibrium the fulcrum reaction should be R is equal to W1 plus W2, that reaction of the fulcrum will be of that its magnitude will be R is equal to W1 plus W2. Now, if you take the moment about fulcrum, that is W1 into D1 is equal to W2 into D2. This must also be satisfied, otherwise seesaw will not be in equilibrium. Therefore, this is the condition W1 D1 W2 D2 is equal to this one. So, that is how that you can, so if a child's weight is less, he can move a distance further and then he can balance. Now, then discuss about the coplanar and concurrent point. In this system, line of action of all forces pass through a single point and force lie in the same plane. An example of is the weight suspended by two inclined strings. In this case, all the forces are in plane. If we can construct a vertical plane, okay, which passes through the strings T1 and T2, and in that case we have got that weight W is acting here and this is point O, and in that case this is the weight is suspended by two inclined system. All the forces are passing through point O, therefore, they are concurrent. The moment of the forces about the point O is 0, therefore, hence second condition is already satisfied and only now you can use the first condition for this one. So, therefore, you have constraint on the forces given by the first this one, that vertical component of the forces should be 0 and horizontal component of the forces should be 0. So, these can be found out. Then the fourth condition is that coplanar non-concurrent forces. Forces can be at one plane, but they need not pass through a point. All forces do not meet a point, but lie in a single plane. An example is a ladder resting against the wall and a person is stands on a rung which is not at the center of gravity. In this case, both the conditions for the ladder need to be checked. So, this is here that in this case you have got to have, it is not center of gravity of the ladder may be different. So, therefore, ladder will also have some force acting. If we make the free body diagram of the ladder, we have to show the reactions of the wall, then reaction of this thing, then at the same time that this weight and this is the things, and then we have to check both the conditions, that is resultant force should be 0 and the moment should be the 0. Then we have non-coplanar parallel forces. In this case, all the forces are parallel to each other, but not in the same plane. An example is force on the table when a book is kept on it. Here on the, if we see on the table, there is a that you know that if we make a free body diagram of the table, I am just trying this one, let us say at the top view of table, here that one has kept a book, but you will replace the book, then you will be getting that the force applied by the book, that is basically W on the table, because if we first consider the equilibrium of the book, then on the book there is a weight and then there is a reaction of the table. For equilibrium of the book, reaction on the book must be equal to W. Therefore, the book also applies load W here, and at the same time similarly you have all reactions F1, F2, F3, F4 acting on this one, then there is a weight of table itself. So, all these forces are there, but they are not in a single plane. Okay, you cannot make a single plane in which all the forces and they, but all of them are parallel, because all the forces are vertical. So, that type of situation is also there, and here you have to check for both the conditions. That means some of the all the forces should be 0, at the same time the moment should also be 0. Then we may have situation that there is a non-coplanar concurrent forces. In this system, all forces do not lie in the same plane, but their line of action passes through a single point. For example, consider a weight W suspended by means of 3 strings. Line of action of all the forces pass through point O. The forces do not lie in a plane. Therefore, the second condition of equation is automatically satisfied in the, because all the forces are passing through point O. For equilibrium, the first condition has to be checked. That means the resultant of the forces must be 0. Therefore, if you resolve the forces into 3 components x, y, z, then the result, sum of the result components in x direction should be 0, sum of the result components in y direction should be 0, sum of the result components in the z direction should be 0. Then the last condition is that our forces do not lie in the same plane and their line of actions do not pass through a single point. They may not be parallel. This is the most general case, and both the conditions of equation 2.1 that need to be checked. That means resultant force must be 0 and its moment should also be 0. Now, let us discuss the equilibrium of coplanar concurrent forces. If all the forces in a system lie in a single plane and pass through a single point, then the system constitutes a coplanar concurrent force system. The resultant all of a system of forces is 0 if and only if its resolved components in 2 orthogonal directions x and y are 0. Moment about the common point of forces is obviously 0, because the forces are passing through the point. So, if you take the moment about the point O, then they will be 0. So, therefore, the first condition has to be seen, that you have to see sigma fx is equal to 0, sigma fy is equal to 0. These two conditions have to be satisfied. Now, these conditions are necessary. That means, if the body is in equilibrium, then sigma fx and sigma fy has to be 0, because assume that there is a force R acting which makes an angle alpha with the x axis. The sum of the resolved components of the forces is equal to the resolved component of resultant. Thus, sigma fx is equal to r times cos alpha, which is equal to 0, and sigma fy is equal to r times sin alpha, that also should be 0 because r is 0. So, therefore, this is this one. So, therefore, this condition is necessary because if r is 0, then naturally the resolved component should also be 0, sum of the resolved components, that means sigma fx is 0, sigma fy is 0. This condition is sufficient also because assume that equation these are satisfied, that means for certain case r cos alpha is 0, r sin alpha is 0, which implies that if you square both and add, then r square cos square alpha plus r square sin square alpha is equal to r square, that must be 0, therefore, hence r will be 0. It is not necessary that directions x and y should be orthogonal, only the angle between them should not be 0 degree or 180 degree. Although it is always that when we resolve the components, we generally take orthogonal directions. Now, even if that angle is different, necessity condition is obvious because the resolved component of a 0 force in any direction is 0. Now, now assume that the resultant force makes an angle of alpha and beta with x and y axis respectively. The condition of equation 2.4 will imply that r cos alpha equal to 0 and r cos beta equal to 0. This provides either r is equal to 0 or r is perpendicular to the both direction, that means either r is equal to 0 or cos alpha is equal to 0. If cos alpha is equal to 0, then alpha is 90 degree, and if similarly here r cos beta equal to 0, that means beta is equal to 90 degree, okay, to this one. So, therefore, if r is perpendicular to both the directions, then either the directions make 0 degree or 180 degree with each other, which is not the case, hence r is equal to 0. To illustrate this point, I present one example. Now, let us consider a body in an inclined plane. Now, this body is kept here and it is acting on an inclined plane r. This is the string tension is T and this is r here. So, here in this case consider a particle of mass m or weight w resting on a frictionless inclined plane. Now, mass is held by a string tied to top end of the inclined plane. Let us choose x axis in the direction of the inclined plane, that means x axis is in this direction, but the y axis is vertical. So, y axis may be like this. Then what happens? If we resolve the forces in both the direction, then sigma fx resolving the forces in x direction, we get t minus w sin theta is equal to 0. Resolving the forces in y direction, we get w minus r cos theta minus t sin theta is equal to 0. Now, if we substitute the value of t from the first equation into the second equation, we get w minus r cos theta minus w sin square theta equal to 0, which gives us w minus w sin square theta is equal to r cos theta. This gives you w cos square theta is equal to r cos theta. Therefore, r is equal to w cos theta. Therefore, we have got r is equal to w cos theta, which we know that is correct, that you have been doing this problem so many times, you have done. So, resultant r in this case will be naturally that w cos theta. So, here we see that we have resolved in two different directions, although in most of the time we will be resolving the forces in orthogonal directions. Now, if the three forces are acting on a body, and then the system of three forces must be coplanar and either be concurrent or be parallel. That is a three force theorem. If the two forces, if just one force is acting on a body, then the body cannot be kept in equilibrium, because just one force is, so the resultant cannot be 0. If the two forces are acting on the body, they must be equal and opposite, and they also must be collinear. If they are not collinear, then they will produce moment. Therefore, in two force theorem is that if there are two forces acting on the body, they must be collinear. Now, we present the three force theorem. A system of three forces in equilibrium must be coplanar and either be concurrent or be parallel. Now, proof of this is as follows. Assume that the two of the forces F1 and F2 intersect at a point A. Supposing they are not parallel and two forces can intersect at a point A, then the resultant of these two forces is given by R is equal to F1 plus F2. Okay, so resultant of these are the two vectors. So, therefore, it must be in the same plane, because one can construct a parallelogram which lies in that plane. Third force is equal and opposite of this force. It must be in the plane containing F1 and F2. If it does not pass through, if it does not pass through the point A, then it will produce a couple. Hence, if two forces intersect at a point, the third force is in the same point and passes through the same point. That means, the third point should also intersect. Otherwise, if you have two forces, they are there and you take their resultant, now the third force may be here, then it will produce the couple. So, therefore, if the forces are non-parallel, but they are in the same plane, then they must be concurrent. Then they must be concurrent. It is now assume that the forces do not intersect. If they do not intersect, they must be parallel. Assume that force F1 passes through point A. If B and C are some points on F2 and F3 respectively, then taking moment about A. Now, if we have it is this one. See, if you have a force F1, this may be F2, and let us say this is F3. Now, this point is A. Here you have got point B, then here you have got point C. Now, let us take the moment about A. Moment of the force F1 about A is 0, moment of force F2 about this is RBA cross F2 plus RCA cross F2 is equal to 0. Now, if M be some other point on the line of action of force F1, then taking moment about M, suppose there is M is this one, then we can have RB M into F2 plus RCM into F3, that is equal to 0. Now, subtracting these from this one, you get RAM F2 cross F3 is equal to 0, because about this one and this okay, and this one. So, therefore, one can always say RBM. So, this is RAM cross F2 into F3 is equal to F2 plus F3 is equal to 0. This is now since RAM is in the direction of F1, we can write F1 cross F2. Okay, there is equal to 0. This implies that F1 line containing F2 and F3, since they do not interact with each other, they must be parallel. So this is the thing about that one. Now we discuss about Ramy's theorem. If the three forces are coplanar and concurrent, if three forces coplanar and concurrent forces acting on a particle keep it in equilibrium, then each force is proportional to the sine of the angle between the other two, and the constant of proportionality is the same. For the system shown in this one figure, P1 divided by sine alpha, P2 divided by sine beta, P3 divided by sine gamma must hold good. So this can be easily proved, that if you have that forces P1, P2 and this is gamma, so P1, P2, P3. So here P1 divided by sine alpha, P2 divided by sine gamma, P3 divided by P1 divided by sine alpha, P2 divided by sine beta, P3 divided by sine gamma. This must be holding good. Now therefore, if we consider the same problem of a inclined block, and this is the block is kept like this is attached by spring T, this is the W, this is R. Okay. Therefore, if you apply Ramy's theorem, then W divided by the angle between R and T, that is W divided by sine 90, then R divided by angle between W and T, that is sine 90 plus alpha, then T divided by sine 180 minus alpha, that means T divided by this is the thing between R and this one. So naturally that this angle be T divided by angle between this and this. So therefore this is sine 180 minus alpha. Therefore it gives us R is equal to W cos alpha and T is equal to W sin alpha. Now when we apply the forces, when the body is there, it also experiences reactions. These are the self-adjusting forces developed by the other bodies which come in contact with body under consideration. Suppose you put a body on the other body, then the first body applies some force on the second body, therefore second body in reaction it supplies the force on the other body. So these are the this one. Suppose you put on a table, if you put a weight, this is being pulled by the gravitational force, it has tendency to go down, but as it tries to go, it will compress this table, therefore table in turn will apply the force that will be called reaction force. Therefore body will not move, otherwise the body would have fallen. But here the weight W is of the body is acting like this, and the reaction of that table is also like this. So therefore this is balanced, this balances each other. When two bodies come in contact, both apply equal and opposite forces on each other, that is comes from Newton's third law. If the contact surface is smooth, the force will be in the normal direction of surface of contact, because if the contact is smooth, there is no frictional force acting here. Suppose this is a block, so therefore no force can come from the side, only the force can be normal. This is not true if friction is present, because there will be a frictional force that will also be acting here. But otherwise, if there is no friction, then when the bodies come into contact, then the force has to be normal, otherwise the body will start moving in the another direction, because there is no friction to constrain the motion. Now, consider the frictionless contact of the following two bodies. You have two bodies, one ball is kept on the other ball. In this case, the contact force will be along common normal. You have common normal of the balls and the contact force will be along that. A ladle example is there. In this case, if I put a ladle which may be having some weight also, in this case the reaction of the wall will be in horizontal direction and that of the floor in vertical direction. So, here the reaction of the wall is shown like this R1, reaction of the floor is in the vertical direction. The this one now if we have a pin joint, then suppose we just make a pin joint, we take a rod and then we pin it somewhere, that so that it can rotate. If we have a floor here and on this we fix up this rod, make a pin. So, this is the thing. So, this is a pin joint. It can supply the reactive forces in any direction, its motion, it can constrain the motion in x, y, but it cannot prevent the movement. But if you have fixed joint, it gives you reactive forces as well as movement, because it does not allow it to move. Okay. It can, in the pin joint, if I put a movement, that means if I act a force like this, then you know that the pin is this link starts rotating. So, this is the thing. Now, we discuss about constraints. Now, a particle can be described by three coordinates in a space. You have, say, in any like Cartesian coordinate system, a particle can be described by x, y, z. So, therefore, we say the particle has 3 degrees of freedom. Okay. Particle can have some x coordinate, some y coordinate, some z coordinate. We can adjust these degrees of freedom by putting constraints. We can constrain, for example, suppose we say that particle is allowed to move in a tube, okay, that very thin tube, it is or on a tube or on a surface of rod, then it is constrained to move only in one direction, its other 2 degrees of freedom has been adjusted. So, we have adjusted 2 degrees of freedom. Similarly, in a rigid body in space has 6 degrees of freedom, because it can be described by 6 coordinates. A rigid body can actually translate that that like this, or it can translate like this. Rigid body has this one rigid body is, suppose this is a rigid body, this block, it can move like this, it can also move in this direction, second y direction, it can also go up and down z direction, this is the third direction, but at the same time the rigid body can rotate about the vertical axis, it can rotate about this axis, this x axis, it can also rotate about the y axis. So, therefore, it has 6 degrees of freedom. So, if you want to describe the degrees of freedom of the body, we need to tell, we can fix up any point here, say let us say this corner point, we have to say that what is its x, y, z coordinate, at the same time keeping it fixed, I can still change the angles orientation. So, this is the thing, see this is this way I can keep the body, I can rotate the body like this. So, we can still change the orientation, that means I can still give the rotation about either x, y and z axis. So, that means a rigid body has got 6 degrees of freedom. So, it can be specified by x, y, z and another 3 angles. 3 coordinates will describe the position of any particles, say central particle. Keeping the position of that particle fixed, the body can be rotated about 3 axes. Thus, for we need to have 6 coordinates are required. If a body is confined to move in a plane, it has only 3 degrees of freedom. If we say that body has to move in a plane only, like if in a blackboard, if I say I am moving my duster, but it should be only on the blackboard, then naturally that it is a motion in a plane, but it can be that duster can be moved along either x direction or y direction, or it can be rotated in the plane itself. So, therefore, it has got 3 degrees of freedom. Other 3 degrees of freedom you have arrested because you can find it to move in a plane. If you make a hole near one end of the one rod and through this hole insert a pin, suppose you insert a pin on this duster, the position of this point gets fixed. However, that duster or rod can be rotated about this point. Thus, a pin joint arrests 2 degrees of freedom. If you in a plane, if you fix up a pin joint in a plane, it is arresting 2 degrees of freedom. So, this is how that you have. Now, constraint means the restriction of movement. Pin restricts movements in 2 directions. Certain type of constraints restrict only 2 degrees of freedom. For example, a roller moving on a plane surface is constrained along normal direction, but not against tangential direction. So, you can have only 2 degrees, or it can be having that only one this one direction. So, suppose you have like this. Now, a roller is constrained to move against tangential direction. So, this is it is not constrained, it is constrained to move, it is constrained to move only along tangential direction. So, the normal direction it cannot move, but in tangential direction it can move. So, you know you have arrested 1 degree of freedom. The fixed support offers constraint against rotation as well as lateral movement. So, they arrest, if you have a fixed support, it arrests all 6 degrees of freedom. In 3 dimension or in 2 dimension, it arrests 3 degrees of freedom. Now, if you have if you consider 2 rods which are fixed by this one, if you have, say, if you have got 2 rods, now let us say that this is the rod and this is another rod, these are the pin joints. Now, each rod, this degree of freedom of this rod is 3, the degree of freedom of this rod is also 3, but you have 3 pins, 1, 2, 3, each one has arrested 2 degrees of freedom. So, therefore, you had total 6 degree of freedom, but they have been arrested. So, 2 into 3, that means this one. So, degree of freedom of this is 0. So, therefore, they are okay. So, these therefore, both the rods are having, hence the degree of freedom of this system will be 0. Now, therefore, this becomes a structure and no particles of this structure can undergo motion. Okay. So, this is about this thing. Now, if a force is applied to the structure, reaction forces are developed for keeping the structure in equilibrium. If when a force is applied to this one, then therefore otherwise the structure will move. So therefore the structure, now can we find out the reaction forces? Yes, since these are there are three. Okay, now here so therefore we can find out this one. Now if we have on the structure, simple structure like this, in this case this is the pin joint, this is another pin. Can we find out this? Because we, these are three non-parallel forces on a body, and we can find out these reactions. Okay, here there are reactions on this pin, that if we consider that there may be some reaction here, then there may be reaction here, and then okay, so these forces. So in this case, so we can find out the reaction forces. The problems which can be found out by statics are called statically determinate, because the forces can be found by applying the equation of equilibrium. These things will be taught in detail in the next lecture on truss. Now here this is the example, that this is rod 1, this is rod 2, and on this, that if you want to find out the reaction, then the rod 1 here, that you have to say like this, and on this you have to find out reactions. This is the force acting on this rod. Only two forces are acting, so therefore they must be collinear, that means they must act along the rod. And here, that you know, it may be some force may be here, and here the reaction components may be F, and another maybe other component may be there. Okay, so that is this thing. So this has to be there will be one equation of equilibrium here. Similarly, you at this point there are rods, one force is like this, and then you may have the another one, and if there is a force applied here, that force will also be shown, and these forces will balance, and therefore you get the another equation. But then the third one, here also you have forces, here you have this is this one, and the other component is like this, and then you have this one. So actually you have got see three pins. You can write, you can resolve the components of the forces in two directions, and you can find out, say you can get two equations, sigma fx equal to 0 for this two equation, then two equations sigma fx equal to 0, sigma fy equal to 0. Similarly here, sigma fx equal to 0, sigma fy equal to 0, and this is at this point you go. Here also you can find out sigma fx equal to 0, sigma fy equal to 0. So there are basically 6 equations, and you have how many unknowns, that two reactions, x component, y component, to this one another x component, y component, and at the same time here that this force itself and the force on this. So 6 unknown, 6 equations. That means you can solve this problem. Now suppose a rod is added as shown in this one. Now the total degrees of freedom of all the rods combined is 9, because each rod has 3 degrees of freedom if it is unconstrained. There is an addition of 2 pin joints, because this is constrained here, then again it is constrained at this end also. So it can be considered as a separate pin. Now there is a, so degree of freedom is basically -1, Why? Because see, we have total 9 degrees of freedom, but now we have 1, 2, 3, 4, 5 pins. So, therefore, each one will suggest 2 degrees of freedom. Therefore, we have 9 minus 10 is equal to minus 1. This is minus 1. There are now 3 reactions here, that you know, this is the thing here. Now, for the whole structure also there are only 3 reactions, and equations of equilibrium are only 2. That means that therefore, we cannot determine these by equations of equilibrium. This problem is called statically indeterminate problem. If we consider the component wise also, that you know that this one, so you have at we can write sigma fx0 sigma y0 here. So, we can have that this thing at this point also we have. So, therefore, what happens that we have 2 equations for this, 2 equations for this, 2 equations for this. So, 6, and we have 2 equations at this pin joint. So, therefore, totally we have 8 equations, but let us see how many unknowns you have to find out. You have to find out that x component of that reaction, y component of the reaction. So, 2 here, 2 here, 2 to 4, 2, 6, and plus these 3. So, you have to find out 9 components, but you have got only 8 equations. So, therefore, naturally this cannot be solved by statics. Therefore, this problem is called statically indeterminate problem. Okay, this is what is that, this one. Now, we have given some simple example based on the 2-dimensional statics. Now, let us discuss something about 3D statics. Now, equation 2.1 is valid for equilibrium in 3-dimensional space also, means there also basically sigma f must be equal to 0, sigma m equal to 0. In 3 dimensions, vector equations and their scalar components may be written as sigma f is equal to 0, or sigma fx is equal to 0, sigma fy equal to 0, sigma fz is equal to 0. That is in the, this is in the scalar form. That means this is a sigma f is equal to 0, but we write that sigma fx 0, sigma fy. So, we get 3 equations here. Then we get sigma m is equal to 0, or mx is equal to 0, my is equal to 0, mz is equal to 0. So, we are obtaining these 6 equations, and we can have this thing. Now, reactions in 3-dimensional cases will be like this. If a member is in contact with a smooth surface, then the force will be normal to that surface. Now, this is the thing. So, in this case, if it is a member is in contact with smooth surface, or it is supported on a or it is supported by a ball, in that case, if we make the free body diagram of that structure, so free body diagram shows reaction force normal to the surface and directed towards the this one member. So, on a smooth surface, the reaction has to be this one. Suppose we put that some object on a smooth floor, then the reaction will be normal to the floor only. And then, however, if the surface is rough, the possibility exists for a force tangent to the surface to act on the member as well as a normal force. Now, if member is in contact with rough surface, this is the thing, the free body diagram showing a force F tangent to the surface as well as a normal force N. This is the thing, this is force F is acting here, and there is a normal force N acting here. So, this is F and this is N, and this is the thing. So, that reaction can be, instead of normal, it can be at other angles also. Now, a bar and socket joint like this, is free to pivot about the center of the bar can support a force R with 3 components. Now, bar and socket joint is this one, it can support 3 components. So, it provides 3 components of reaction RZ, RZ, Rx and Ry. So, free body diagram is shown here, and a fixed connection can support a couple M represented by its 3 components as well as a force R. So, force R is also provided and couple is also provided. Couple can have 3 components. So, this is Rx, Ry, Rz, Mx, Mz and My. So, you have to know that what are the reactions coming on this one object. If you make the free body diagram, you must know not only the applied forces, but also the reaction forces which the other body supplies because of the interaction of that object with the other body. Now, this figure shows a laterally constrained roller moving on a rail. Roller or wheel supported with lateral constraint. It is constrained to move that in this direction. It can move in this direction, but it cannot move down, okay, because of the constraint of the rail, and this cannot move this one. So, therefore, roller are support with lateral constraint, and it is also supported with it cannot move sidewise as well, because there are, you know, that here supports have been provided. So, therefore, what happens that this is the reaction force is in the direction of upward direction N, because it is constrained to, it is not allowed to move in the direction that it is this rail is not allowing it to move. That means, rail is applying some reaction, that is why it is not able to move down, and similarly it is not allowing it to move sideways. So, sideways even if we apply some force, therefore, that means rail is applying some force P in this direction. So, therefore, that this is the P. So, these are acting on this one. Now, here so in this thing, but in this direction you do not see any reaction force, because if I apply a force, it will simply move, there is no constraint. So, nobody is applying any reaction, that is why it is moving in this x direction, that is the thing. Now, this figure shows a thrust bearing supported on a shaft. Now, this is a thrust bearing support. Now, here this is x, y and z. After here in this case there is it is constrained not to move along x axis. This rod cannot move in the x axis, even if I apply some force it will not move. So, therefore, what happens that there is a reaction Rx which the walls of that hole or that this one bearing are supplying. So, therefore, bearing gives a reaction in direction x. So, therefore, this is Rx. Similarly, it cannot move in the z direction either. So, therefore, there must be another reaction Rz, okay, that is shown here. Although I have shown it upward, in some cases it can be downward also. So, this is what that this thing is there. Similarly, that but in this direction, if I do not allow it to move in that direction, if I have put some support, then there will be a reaction Ry also, and at the same time this is not allowed to rotate about x axis, therefore, reaction moment Mx is there, it is not allowed to rotate about z axis, therefore, reaction moment Mz, but it is allowed to move along y, therefore, there is no reaction moment in that direction, it can only rotate. So, this is a thrust bearing support, and this is the free body diagram of the shaft shown. So, this is what that it has this one. Now, we may have that apart from that we have discussed about equilibrium conditions, very briefly we discussed about another type of method, that is concept of the virtual work. Equilibrium conditions can be obtained from virtual work principle also. The work done by the force F during the displacement dr is defined as du is equal to F times dr. The work done by the couple of magnitude m during the displacement d theta is du is equal to m d theta. Now, what is a virtual work? Consider a particle whose static equilibrium position is determined by the three forces which act on it, any h times delta r. For an assumed virtual displacement delta r of the particle away from the equilibrium position, the total virtual work done by the particle is this one, sigma f dr, that is the condition. Since the particle is in equilibrium, sigma f is 0, the equation delta u is therefore an alternative statement of the equilibrium condition for a particle. That means virtual work done on the particle must be 0. This is for a particle. I have told about the virtual work principle also. So, today we discussed about the equations of equilibrium.